Okay, so now we're going on to functions, right? So I talked about this a little bit when I was doing the code breakdowns, whether you have or haven't watched this yet. It isn't really important because we're going to get to pointers. And so really one of the main reasons people use pointers is because you need to access some sort of information from inside a function. So to understand why a pointer is used, it's sort of worthwhile to explain a function. Now, I haven't seen these slides yet, so I probably should have looked at them before, but we'll just sort of wing it, right? So as the first line says, like C programs consist of functions that call each other. And so what that means, if you look at the assembly, if you don't have really much knowledge of assembly, I went through the context switching in my RTOS lectures and you have this program counter, and it points to the next instruction in memory. Like as you can imagine, you compile a binary, which is essentially just a ton of assembly instructions, and these are loaded into memory, and then they get read, right? Like sequentially, your program's in memory sequentially, and it just steps through it and runs it. And then sometimes when you go into a function, the assembly will tell this program counter to go somewhere else in memory, like where the function is stored. And this is also why you can have function pointers, because the function is just stored somewhere in memory. It has a memory location just like a variable. But when you essentially hit the assembly instruction that tells the program counter to go somewhere else, this is you entering this function. And so the function has also like a stack, and so this is sort of like the important thing that's really important to know, that when you go into a function, everything that's passed into it, these like parameters, they're actually put onto this stack. Okay, and so hopefully these okay, I'll skip this. They call each other, has no parameters. So yeah, obviously we can see here, this is a function called foo. It has no parameters. And this is a foo, and it returns nothing, as this description says. This one, the difference is you have an int return, so you need to return an integer. And so usually, just for as a side note, 0 is generally success. We'll say even better. Generally 0 is no error. And usually -1, but sometimes also 1 is an error. Isn't an error. And this is more so just saying error. Better said, not 0 is an error, right? Because this way, usually people use 0 for no error and a number for error, because then you can use error codes, because you can actually check what number it was and you can get some related error code. But generally, if it's got an error, you return a value. If it's no error, you return 0. So I think what I wanted to get to is not really covered in these slides, because this is very basic how you write functions. But I want to look at only function exactly. This is where it's like this prototypes linking and whatnot, headers. So this is what I think should be hopefully known to all of you. Yep. Read this if you want another reiteration about copy and pasting. The preprocessor functions like this may not be available in embedded systems. Exactly. Variables. Okay, now so I'm just gonna have to make this slide up here. So I wonder if I can insert a slide. Edit or somewhere journal. Here, page. No, okay, don't want. So what I want to get to about pointers and why functions, because if we have here like this variable into, we see it here. We can see our function is defined here as that this variable, this argument passed in, is used in the calculation of the return value. So you can call it passing this variable, like you pass in 2, and it's used in the function. Now what happens on like a lower level is that this function, this value here, is passed in here, for instance, as 2, and this 2 is used in the assembly. I'm pretty sure it's put into the registers, or it's saved somewhere in memory and pointed to as an argument, because the arguments are stored separately in memory. But what happens is when you go to the function, you actually get a stack of memory that's allocated to the execution of that function, and the argument gets copied into this stack. So the memory, like this variable 2, is saved into the stack of the function, but it's copied. So you've actually got a separate copy of 2 in memory. And the problem is that because you have this copy on the function stack, when you return the function, this stack gets destroyed. It gets popped. And the variable copy also gets destroyed. Now, this is why the return, so you have, the only really way you have of giving information back from this stack is to return the new value. So if we had a function, if we had, say, myfunc, and it took in a number, and the one way we can get the number to be returned is to return it here. We return an integer. So our function would return I, right? So it would increment I, and then it would return it, meaning that, and then we can use this function if we want to say we have some int, we'll have some int a here, whatever, a equals 0. This is int a equals 0. And we can say a equals my func a. And so this would copy in a, so a's value would be copied into I, so this is the local copy to the stack. It would get incremented, but then the new incremented value would be returned, and we then set this into a. So we sent a in, we incremented a copy of it, and then we set a equal to the value of the copy which was returned to us. So hopefully this makes sense. But now the problem is, what happens if we can return if we wanted to modify entire structures or something, we can send in the struct, we can then modify it, and we can return a copy of the modified struct. But this isn't very efficient, or it can be a bit tricky, and it's very cumbersome doing this returning of things and setting variables to new copies of things and whatnot. And so why we want pointers, which I'll get to in a second, is because we can pass in this integer, we can pass in a memory address. And we can say, go to this memory address and modify the variable that's at this memory address. Now, when it returns, the variable storing the memory address gets destroyed, but this memory address and the variable at that memory address still exists in memory. And so once the function returns, whatever we did at that location in memory still happened. Nothing changes. And so this is what I'm trying to get at with functions, how they tie into pointers. By using pointers passing into function, we can pass it memory addresses where it should modify, so that when the function returns, the modifications have still happened, and they haven't just been lost because the function's returned and its stack has been destroyed. So I think I'll stop this one there. I don't think I'll really go through the variable stuff here. I'll put these slides up online as well. I don't think that this is really, you should all really know this, but we're going to get to pointers now, and we'll see why the function stuff I just mentioned is very important. So.